In section 12.9, we're going to learn a different method for dealing with constrained optimization problems. That is the method of Lagrange multipliers. This will be for working with optimization problems where there is a constraint on the variables. You'll recognize these problems as problems you've already learned how to do these. We've already done these in a couple different methods, but this is going to provide an alternative method for solving these problems, and it's usually a quicker and algebraically easier method to do. So we have our objective function, which is right here. So let f of x, y, and z be the objective function, the thing we're trying to optimize, right? So that's what the objective function is, right? So this is to be optimized. And then g of x, y, z is our constraint, right? That's our limitations, right? We are constrained, we are limited by whatever is g of x. And notice that it must be equal to 0. Okay. Well, then the solutions to the system of the gradient of f is equal to lambda, that's a Greek letter lambda, times the gradient of g, and g of x, y, z is equal to 0, will optimize the original function. Now, lambda is just going to be, how do I put this? It's the Lagrange multiplier. And you sometimes find it, you sometimes don't. You use it, it's part of the process. Your answer won't involve lambda per se. It's just part of the process of dealing with this. All right, so let's practice. Actually, we're going to do this twice. So we're going to perform this problem once using the methods from Calculus 1. And then we're going to do it again using Lagrange multiplier method. All right, so let's start with Calculus 1. All right, well, we've got a constraint here. So we want to find the minimum and maximum values of this function. So you can see this is the objective function right here. I mean, it says it wants the min and the max of this function right here. So that would be your objective function. Right, so right here, objective function, such that x squared plus y squared is equal to 4. Well, that's your constraint right there. Okay. So what do? Well, we take our constraint here and we solve it for one of those variables. And it kind of doesn't really matter which one. I'm going to solve it for y. So y squared is equal to 4 divided by x squared. So if I take the square root of both sides, y is equal to plus or minus the square root of 4 over x squared, which means y is plus or minus 2 over x. So I'm going to take that, I'm going to substitute it into my objective equation. So we will substitute. And of course, because it's a plus or minus, I'm going to have to do everything twice. All right, so case number 1, actually I'll do it this way. Case 1, I'm going to use y is equal to 2 divided by x. Seems reasonable. All right, so my objective function f of x, y, is going to become f of x 2 over x, which is going to be x times 2 over x plus 2 over x, right? Wherever there was a y in the original function, I'm turning it into an x. That is equal to 2 plus 2x to the negative 1. Now I'm looking for the minimum and maximum. If you remember, we learned in Calculus 1 that those values will happen at critical points. And critical points are when the derivative is equal to 0 or undefined. Okay, so let's see here. If I want to take the derivative of this, f prime of x, right? There's now only x in here, so this is f of x now, right? We got rid of the y. So f prime of x is the derivative of this. Well, the derivative of 2 is 0. The derivative of x is 1, and then this will become minus 2x to the negative 2. In other words, it is 1 minus 2 over x squared. And the critical points will be when that derivative is equal to 0. So I can put the equal 0 part over here. So I can say 1 minus 2 over x squared equals 0. That means 1 equals 2 over x squared. That means x squared equals 2. That means x equals plus or minus the square root of 2. Well, those aren't the critical points. Those are just the x values of the critical points, because this is in the end ultimately a two-variable function. So I would need to find the y that goes with it. But notice y is equal to 2 over x. We set it right here at the top. There we go. So that would mean y is equal to 2 divided by the square root of 2. Or 2 divided by the negative square root of 2, but I just want to get over here. So what's going to happen is this is 2 square root of 2 over 2, which is the square root of 2. So your critical points, and there was nothing special about this being positive or negative, so I'm just going to kind of put a plus or minus. So our critical points are square root of 2, square root of 2, and negative square root of 2, negative square root of 2. All right, so now we have to do it all again. So case number 2 would be that y is equal to negative 2 over x. Okay, so then let me just do this in a different color just to kind of keep everything straight here. So then we would have f of x comma negative 2 over x, which becomes x times negative 2 over x, let's see, plus x plus negative 2 over x, which is negative 2 plus x minus 2x to the negative 1. And this becomes an f of x now. And the critical points will happen when the derivative is equal to 0, so I need to find the derivative, which is 1 plus 2 over x squared. All right, so the critical points happen when, let's see, 1 plus 2 over x squared is equal to 0. That would mean, let's see, 2 over, well, I'll just say it this way, 1 equals negative 2 over x squared, so x squared equals negative 2. And that's not possible. Well, it's not real, let's put it that way. It's possible, but not in the real number system. So we stop right there. So then we would go make a table. We make a table with our critical points. We can kind of go either way. So critical points, and then our f of x, y values, and then our conclusions down here. Well, the only critical points we have are square root of 2, square root of 2, and negative square root of 2, negative square root of 2. So you plug these points into the original function and you get a value. So square root of 2 times square root of 2 is 2, plus the square root of 2 plus another square root of 2. So that's 2 plus this 2 square root of 2. So 2 plus 2 square root of 2 for that one. And then this one, let's see, it'd be negative square root of 2 times negative square root of 2, right, which is positive 2. And then minus the square root of 2 minus another square root of 2. So it's 2 minus 2 square root of 2. Well, this is bigger and this is smaller. So we have an absolute max at, and it would be square root of 2, square root of 2, 2 plus 2 square root of 2. And then we have an absolute min, sorry, I ran out of space there, absolute min at the point, let's see, negative square root of 2, negative square root of 2, 2 minus 2 square root of 2. There we go. All right, so that's what we did in Calc 1. And of course, it's very akin to what we were doing in Calculus 3 earlier. So we've already used this method. So we could say using methods of Calculus 1 and earlier, I'm spelling that wrong. Calc 3 sections. In particular, section 12.8, if you are in the newest, or in the old edition, or I think it's 15.7 in the third edition. Okay, so now we're going to do it all again, but with the Lagrange method. So this was not this method. This was, hey, doing this old school. And now we're going to compare it to the new method, the Lagrange method, which is a different method that is set up for you right here. Okay, so let's see. We have our objective function. It's still right here. We still have our constraint right here. The problem is, if you remember in the method, it said the constraint must be set equal to 0. So we're going to actually rewrite that into g of x, y is x squared y squared minus 4 equals 0. That is the constraint we will use, right? It must be equal to 0. Can't stress that enough, otherwise it won't work. All right, so we're going to do the same problem, but a different method. So we know what the answer is going to be. It's going to be, square root of 2 and square root of 2 and so on. I think I spelled Lagrange slightly wrong. I think it's supposed to be lowercase g. All right. Well, Lagrange method says that the gradient of f is equal to lambda times the gradient of g, where f is the objective function right here, and g is that constraint function. But the constraint function has to be set equal to 0. Okay, so gradient of f. Gradient of f is f sub x and f sub y. And that's all there is to that. Here, I'll do it in purple because my objective function was purple. And that's equal to lambda, some unknown constant scalar thing. Lambda is just some number, right? Some scalar. Times the gradient of my objective function. Well, or excuse me, my constraint function, which would be g sub x, g sub y. Right? That's the Lagrange method. Okay, so let's find some derivatives. So f sub x would be the derivative of this with respect to x, which would be y plus 1. So y plus 1, comma, x plus 1 is equal to lambda times, all right, and then the derivative of this with respect to x would be, bring the 2 down, so it's 2xy squared. The derivative of 4 is 0. And then derivative of that with respect to y is 2x squared y, or 2yx squared, like that. Now here's the trick. So these things have to simultaneously be true. In order for that to happen, this piece right here would have to be equal to lambda times this piece right here. So that means that y plus 1 is equal to lambda times 2x squared y. And at the same time, let's see here. I'll use green. This piece is equal to this piece times lambda. So you'd say x plus 1 equals lambda times 2yx squared. These things both have to be true at the same time. Now lambda is the same lambda on both of them, and that's what we're going to use to solve this. Sneaky, huh? So lambda over here is equal to y plus 1 divided, because that's multiplication right there, divided by 2x squared y. And at the same time, lambda is equal to x plus 1 over 2yx squared. Putting those two pieces together, because they're both equal to lambda, that means that they're equal to each other. And that means that y plus 1, or excuse me, x plus 1 over 2yx squared is equal to y plus 1 over 2x squared y. Right? Because they're both lambda, and lambda is equal to itself. Now, to solve this, you could use a couple methods, but I mean, I can use cross multiplication. This is a proportion. So y plus 1 times 2yx squared is equal to x plus 1 times 2x squared y. Now you can divide out what they have in common. You could also have factored it or not have bothered distributing it in the first place or proportioning it in the first place. But either way, I'm going to divide everything by a 2 and an x and a y in order to make things cancel. That's my goal. So the 2xy will make the y, and one of the x's disappear here, make the 2 one of the x's, and the y's disappear here. Oh, and it just occurred to me, I did this wrong. I should have too many y's. All right, hold on. Right here, it was 2xy squared, so this is 2xy squared. You were probably yelling at your screen, you know. So this is 2xy squared. It's really good I color-coded this. It makes it easier. So this is 2xy squared. So that makes this 2xy squared. So it's going to make one of those y's disappear, but not the other one. So it's going to make the power of 2 disappear when I divide by 2xy. So I'll lose the 2, I'll lose the x, and I'll lose one of the y's. So I have this x left, I have this y left, and then I have the parentheses left. So let's think about what that means. That means y plus 1 times x equals x plus 1 times y. Okay, I'm going to lose color. So this is xy plus x equals xy plus y. Subtracting xy from both sides. The only way this is going to work is if x is equal to y. Okay, well, using the constraint equation, right, let's take that. So if I know that's the case, I need to get some answers here. So use the constraint. I know that g of x comma y is equal to 0. That means that x squared y squared minus 4 is equal to 0. If x is equal to y, that means that x squared times x squared minus 4 is equal to 0, which means 2x squared equals 4, which means x squared equals 2, which lo and behold means x is equal to plus or minus the square root of 2. Look familiar? And therefore y is also plus or minus the square root of 2 because x and y are equal. And I have my critical points again. Actually, I'll put them here. Let's see here. Square root of 2, square root of 2, and negative square root of 2, negative square root of 2. It all looks familiar, doesn't it? It's a different mathematical way to get to the same thing. Usually the algebra in here is easier than this piece right here. That's the trick. It's not, and in this particular case, it actually was about the same either way. So this one's not really particularly easier. I mean, it's just another way to get to those same answers, to get the square root of 2, square root of 2, negative square root of 2, negative square root of 2. So the Lagrange method gets us there in a different path. But we still have to make this table at the end. That table part doesn't go away. That's still part of it. So you make a little table. And you know you have square root of 2, square root of 2, and negative square root of 2, negative square root of 2. And then you have your f of x, y values, which we already know. This is 2 plus 2 square root of 2. This is 2 minus 2 square root of 2. And so your conclusions are exactly the same. We have an absolute max. We have an absolute min. So that piece doesn't change. What Lagrange method is doing is changing how we get to those critical values. Another nice piece is that it avoids the long derivative and it avoids the substitution. So it avoids some things that the other method uses. Sorry, this is square root of 2, square root of 2, 2 plus 2 square root of 2. And this one's negative square root of 2, negative square root of 2, and then 2 minus 2 square root of 2. And this particular example is kind of even in the amount of work, but the next one I believe is considerably easier with the Lagrange method. So let's see that in the next video.